This example is about showing how sigma W can be used to simulate staged construction. In addition, we'll use this example to illustrate the use of infinite elements, and we are going to show with this example how to define undrained strengths that increase with depth and are defined as a function. The same with the Young's modulus E. We're going to use a total E that increases with depth, and then the main purpose is to illustrate how to simulate stage construction. In most soft soil sediments, the undrained strength tends to increase with depth, and the reason for that is that at greater depths down here, there's a higher overburden stress. The soil is consolidated to a higher stress level, and consequently therefore has a higher undrained strength at depth than near the ground surface. The same is true for the stiffness of the soil. At the bottom of the layer, under higher stress levels, the soil tends to be stiffer because it is consolidated to a higher stress level, and so the stiffness, the total Young's modulus, generally tends to increase with depth. We simply say the stiffness increases with depth, and in this example we'll show how these functions can be defined in sigma W. A few comments then about the use of infinite elements. Infinite elements are sometimes a convenient way of extending the far field boundary of a problem, and in sigma W it is the left and right far field boundaries. These elements, while they can be very useful, they must be used with considerable care. Generally, infinite elements should only be treated as linear elastic. That is to say that we should not assign nonlinear behavior to infinite elements. Basically, you can think of infinite elements as springs. The far field boundaries of the problem, in essence, have spring-like behavior when we use linear elastic properties for the infinite elements. Furthermore, often it's preferable to use total stress property parameters because they ignore any change in pore pressure in the far field. This is not totally necessary. We could use effective drain stress parameters in the far field and make use of pore water pressures, but there would be no change in the pore water pressure in the far field infinite elements. Most importantly, however, is that the boundary condition should be zero displacement. Repeating, they should be zero displacement. We should not apply stresses or forces to infinite elements on the boundaries. They should be zero displacement. Even specifying a non-zero displacement is not a good practice with infinite elements. So generally, we start without infinite elements, and then toward the end of a modeling exercise, we may add the infinite elements to see whether it makes a great deal of difference on the solution. But generally, the rule is, when in doubt, leave them out. So don't use them without understanding the full implication of what they are all about and how they behave. And if you're in doubt as to the behavior of the infinite elements, you can extend the mesh to the left and right rather than use infinite element if that is more comfortable for you. So here is the exercise for stage construction. We're going to start by establishing the in situ stress conditions. Notice that we have a water table at the original ground surface, As a result, we will have to use effective drain parameters in order to get the total stresses correct. And then we're going to switch to total stress parameters for the loading phase. During the fill placement, we will treat the foundation as an elastic plastic soil behaving in an undrained manner. We will use total stress parameters. The undrained strength will vary from 100 at the top of the layer and increase linearly to 500 at the bottom. The stiffness will be 5,000 kPa at the top, increasing to 15,000 kPa at the bottom. And during construction, we are going to treat the soil as behaving in an undrained manner. And since the soil is below the water table, it is fully saturated. And an undrained soil, when fully saturated, the thinking is that when a load is placed on the soil, that the change in stress in the vertical direction will be the same as the horizontal direction. That is, water is incompressible and most of the load goes into the water, and consequently the changes in stress are the same in both directions. To simulate this behavior, we need to specify Poisson's ratio as 0.495, the largest value that is permissible in sigma W. When we specify a Poisson's ratio of a half, so to speak, it is in essence saying that there will be no volume change. When there is no volume change, then the change in stresses in the vertical and horizontal direction will in essence be the same. The infinite elements will treat as linear elastic and use the same Young's modulus function as for the foundation soil. We're going to place the fill in 8 different lifts using a linear elastic material. The stiffness is 10,000 kPa, unit weight 20 kilonewtons per meter cubed, a Poisson's ratio of a half. The soil is deemed to be unsaturated, and any appropriate K0 value like a half is adequate for this illustrative purpose here. And in the end, what we want to do is plot the settlement along the original ground surface, and then also to plot the settlement profile at approximately the center line of the embankment. Going to GeoStudio then and opening file SIG03. The problem has already been defined. All the regions have been defined. The infinite element regions have been defined. We will start at establishing the in situ stress state before we start placing on the embankment. In the earlier session on in situ stresses, we described why it is necessary to use effective drained parameters when we establish the in situ stresses when their soil is below the water table. So in this particular case, going to key in materials, we have a special material here, properties for in situ analysis, that we are going to use in order to establish the in situ stresses. Notice that we have used effective drained parameters, and making it a linear elastic soil is more than adequate. As we have noted in the previous session on in situ stresses, that the Young's modulus is not important, so any approximate value is adequate for the in situ phase of the analysis. And then we have given it a unit weight of 20 kilonewtons per meter cubed and a Poisson's ratio of 1/3. And if you remember the earlier discussion on specifying K0 through Poisson's ratio. A Poisson's ratio of a third represents a K0 of a half condition. So that is the material that we will use to establish the in situ stress state. The material has already been applied to the regions. Notice that we have two regions at the ends of the problem, which are the infinite element regions. Very briefly, to create infinite element regions, you say draw regions, and at this point you can select infinite element regions. Once again, if you're more interested in the use of these elements in your problems, I would refer you to the Sigma W engineering book for more details. Notice that we are using the same material throughout. Under the Key in Analyses dialog box, notice that we are using the initial pore water pressures from a water table. And again, notice, as we've shown before, that the analysis type is in situ. The analysis type is in situ. At the base of the problem, the boundary is fixed in both the x and y directions. At the ends of the problems, we are saying that we will constrict the horizontal displacement but allow vertical displacement. Clicking on Verify, we notice that there is sufficient information to run the main solver. Clicking on Solve, we can solve for the in situ stresses. And going to the results view, if we plot the total vertical stress, you can see the results there. And since we spent a great deal of time in another section interpreting the in situ stresses, we won't repeat that in this exercise here. Going back then to the define view, we have now established our in situ stresses, and now we can switch over to a new analysis, Key in Analyses. Let us clone the in situ analysis and rename this first lift. And this will be a deformation, a low deformation type of an analysis. Notice that we are selecting low deformation type of analysis. Low deformation, and our parent will be the in situ stresses. We are going to get our initial stresses from the parent, and we are going to get our pore water pressures, which we now will say are none. We are doing a total stress analysis, and there I'm going to use total stress parameters, and therefore we are saying we want to ignore the pore water pressures during the loading phase. We use the water table only to establish the correct total stresses. If you recall, the reason we needed to do this is to establish the correct horizontal total stresses. So in this case, we will not deal with any pore water pressures. We will deal only with total stress parameters. Defining our materials then, key in materials. And for the loading phase, our foundation material, we are going to use total stress parameters, elastic plastic. Secondly, our modulus will be a E total, and we are going to use a function, and the cohesion or undrained strength will also be a function. Defining our soil stiffness, then, we click on the ... to define our function, and we add a new name to the function and say foundation stiffness. And we want to have total E versus the Y coordinate. Notice that we are selecting here Young's modulus versus the elevation. So this is the type of function, total E modulus versus Y, and it's a data point function, and we can type in here at elevation 20, total E, we said, was equal to 5,000 kPa. And at the bottom of the problem, elevation 0, the total Young's modulus is 15,000. So here we have the variation of, at elevation 20, at the top of the layer, Young's modulus is 5,000 kPa, and at a depth elevation of 0, Young's modulus is 15,000 kPa. I will correct the name of my function here, switching the D to an F, foundation stiffness. And you always notice that you can go to options and alter the font and other variables. You will notice that in this case you cannot rotate the graph, and there's a reason for that we will discuss sometime later, but Y has to be on the horizontal x-axis. So now we have defined our foundation stiffness as a function of depth. Very important, now we have to assign the stiffness function to the material. Doing the same thing with the undrained strength, we click on ... and creating a function. So this is the undrained strength. Once again, we want to select total cohesion versus the Y coordinate. And it is a data point function. Once again, at an elevation of 20 meters, the undrained strength or cohesion is 100 kPa. And at elevation 0, the undrained strength is 500 kPa. And so now we have a linear variation of undrained strength with depth, and once again we have to assign the function to the material. Notice that our foundation material, we are using a Poisson's ratio of 0.495 to simulate undrained behavior. The infinite elements, they are total stress parameters, linear elastic, and we are going to use a function, and the function will be the same function for the stiffness with depth as what we used in the other foundation soil. And other than that, it is very similar, except that it is linear elastic, representing spring-like behavior, and we can use the same modulus function with depth as we do for the other soil. Now the foundation material, we are still using, for the embankment material, we're still using total stress parameters, linear elastic. This time we're going to use a constant Young's modulus and a Poisson's ratio of 1/3, representing K0 conditions of 1/2. Now we are at our analysis first lift, so we have to change the material type for the foundation, draw materials. We have our foundation material, we have our infinite element materials, and we are going to place the first lift, assigning to it the embankment material for the first lift only. Lastly, we have to change the boundary conditions on the far field, saying draw boundary conditions, and we want to apply fixed in both the X and Y directions on a line at the far field. Running verify, we have an error message. We have to go back to the analysis, key in analysis, and again, this is not real time, but clicking on the time tab, we simply want this to represent load steps, and so the duration is a unity, and we have one step, and as a result, we are going to save the results at this one step. Now to repeat, this is not real time, and so the second units is not important here, but we still have to simulate pseudo time where we apply step numbers. Clicking on verify, we notice that the error and warnings have disappeared, and we can now analyze this case for when the first lift has been placed. And solving the first lift, going to the results view, we have our deformed mesh. It must be at a very large exaggeration factor. Say draw vectors. The default here is a magnification as 100. Let's rather make it a magnification of 10. The results are not all that interesting at this stage, but we will then return back to the results after we have placed some more fill. At this stage, it's useful, however, to look at the results just briefly to make sure that they somewhat appear reasonable before we proceed on placing the other lifts. Going back to the define view, we are now ready to simulate the stage construction. We go to the Key in Analyses dialog box. We clone the first lift, call it second lift. The parent now becomes the first lift. The parent is the first lift in this analysis when we place. So we have defined the analysis for the second lift. And then to simulate the placement of the second lift, we say draw materials, and we are selecting our embankment material on the second lift. And if the icon to illustrate the gravity load is turned on, then you will see that the second lift now is cross-hatched, indicating that the gravity load is only applied to the second lift. Now we can go through and do this same procedure for all the lifts. Going back to the key-in analyses, we clone the analysis again, call this the third lift, and now the parent is now the second lift. So now the parent is the second lift in our analysis called the third lift. Once again, now we need to apply the material, draw materials, and selecting the embankment material for the third lift, and now the third lift is cross-hatched, indicating that gravity load is applied, or the self-weight is applied to the third lift. Now at this stage there are personal preferences as to the route that we can follow. Going back to the key-in analyses dialog box, we could set up all of the analyses and then go and apply the materials, or to do it one lift at a time as we have done here. So we can now say add, clone, call this the fourth lift, the parent now becomes the third lift, and we could also at the same time again say clone, calling this the fifth lift, and the parent becomes the fourth lift. Now you will notice that when we go to apply materials, we now are in the third lift, has already been defined. Now the fourth lift, we say draw materials, selecting the foundation material for the fourth lift. Then we go to the fifth lift, but notice that the fourth lift is not present yet. So we have to say draw materials, selecting the embankment material on the fourth and the fifth. But notice that it is only the fifth layer that has the cross-hatching where the self-weight is applied. So in this case, it is pretty simple to set up all the analyses first and then apply the materials. However, in many cases, to set up all the analyses first and then apply the materials gets rather laborious. So it depends on the problem and the nature of the problem as to the route that you follow. As a general practice, it is best to go stage by stage and make sure that each analysis is completely defined before moving on to the next case or to the next lift. So we now have the fifth, now we're going to 6, 7, and 8, and in this particular case it is fairly simple to go back to the analysis tree, and we now say again clone, and we make it the sixth lift, and the parent now becomes the fifth. We clone again, calling it the seventh lift, and the parent becomes the sixth lift, and finally we clone one more time for the eighth lift, and the parent becomes the seventh lift. So we now can see our complete analysis tree, and we notice that each one depends on the previous lift. And if your thoughts go back to the incremental formulation, each one of these computes a change in stress and adds it to the parent. Add change in stress, adds it to the parent. And this the way the stresses accumulate and the deformations accumulate as we simulate the staged construction. Going back then to the fifth lift, we saw the cross-hatching. Now we go to the sixth lift, and we go draw materials. Our foundation material is the sixth lift. Going then to the seventh lift, we say draw materials for the sixth and the seventh. And finally, we go to the eighth lift, draw materials for the sixth, seventh, and eighth, and the cross-hatching is now applied to the eighth lift. Clicking on Verify, we notice that we have defined sufficient data for the main solver to make some calculations. We can now go to the Solve window, and we have the second through to the eighth that are not solved. There are several different ways. You can right mouse click and say select all. And when we select all and close the solve window after each analysis, sigma W will start at the top of the tree and go through each one of the analysis in turn. This can become extremely convenient when you have done an analysis and the problem has many different analyses, and you've made some material property changes, and then you would like to quickly rerun all the analysis. If it's a big problem, you can select all the analysis and then take a break and go for coffee or whatever, but it is one of the more convenient features associated with the analysis tree is to resolve all the different stages in the proper sequence in turn. Now that we have done all of the solves, we can go to the results view and briefly look at some of the highlights of the results. First of all, it's interesting to note how the infinite elements have compressed and have acted here at the end like a spring. What we are showing here is what we call a deformed mesh. Say draw vectors. We could instead look at arrows, displacement vectors, as opposed to a deformed mesh. And then we can control the magnification of the displacement. In this case, we are plotting the displacement at a magnification of, or exaggeration of, 10 times. The point of the exercise was to plot a graph, and in this case we wanted to plot the ground surface settlement and heave along the original ground surface location. So we are looking at the vertical displacement from toe to toe of the embankment. And we can select the displacement. Obviously, at the in situ level, it is 0. Holding down the control key, we can then plot the displacement after the first lift has been placed. it is rather interesting that the maximum displacement or vertical settlement is towards the toe area and is not under the center of the embankment. Holding down the control key, we can then add each one of the lifts, the second one, the third one, fourth lift, finally the fifth lift, but now we notice that we are approaching the point as the height of the embankment has increased that the maximum settlement tends to be under the crest of the dam. And finally, when we place our last lift, is the settlement profile after the embankment construction has been completed. But we could also look just at the last settlement profile, and we notice that we have significant uplift outside near the toe areas of the embankment, and the maximum settlement is approximately 0.2 meters right under the crest of the embankment. Just one way of viewing the results. Another way is to look at the vertical settlement along a profile near the center line of the embankment. In this particular case here, we are looking at the vertical settlement on a profile down near the center of the embankment. We are plotting here y displacement versus the y coordinate. And it is rather interesting that the maximum settlement occurs somewhat just above the original ground surface. Here is the original ground surface, elevation 20. Here is the maximum displacement. It shows a little bit of displacement here at the top. This is because it is the amount of displacement that has resulted from the calculation of placing the last lift. Nonetheless, it is rather interesting that we have the maximum displacement when we simulate stage construction at or near the bottom of the embankment. This then brings us to the end of this illustrative example illustrating how we simulate stage construction, how we can handle undrained strength and stiffness with depth, and illustrating the use of infinite elements.